All right, this is the last video for section 2.6, absolute value functions. So far we've talked about these special functions. We started out by talking about the piecewise functions. Second one was the step functions, and now absolute value functions. Okay, absolute value function. You know what an absolute value does? It just makes anything positive. If it's already positive, it keeps it positive. If it was negative, it makes it positive. When you graph them, you can think of it as a piecewise function because it really is made up of two parts. For the most part, like right now, we're just going to be dealing with linear functions as far as an absolute value graph. So there are two parts to it. The first part is when you're dealing with x values greater than or equal to 0. If you are, you're just looking at the slope of whatever's inside that absolute value, okay, the positive of it. When the x values are less than 0, you've got the opposite slope. Okay, so right now, slope of this part is 1, slope of this part is -1, the opposite slope. Now, because those slopes are opposite, you're always going to have this V shape. You look at this graph, it looks just like a V. Okay, that is very characteristic of linear absolute value functions. And we may get into having an absolute value of a quadratic, that kind of stuff. It does some similar things, but it does not have a V shape to it. All right, so to graph this, what may be helpful is just making a table. We can graph these things on a calculator, and I'll show you how in class, but let's just start by just making a table, getting some practice with the absolute value. So for some x values, we're going to pick some positive, some negative. -2, -1, let's go -3, -2, -1, 0, 1, and 2. So when we plug in -3 for x, our absolute value makes that positive, so we got 9, 11. All right, -2, that becomes +2 times 3 is 6, 8. -1, that becomes 1, 3, 5. When we plug in 0, we get 2. When we plug in 1, back to 5. When we go to 2, 6, back up to 8. And I'll just throw in this one, you'll get 11. Okay, so now let's just plot some points. So, -3 up to 11, let's just say it's up here. -2, 8. -1, 5. I got to exaggerate these a little bit. I have a bad scale on here. 0, 2, 1, back up to 5. 2, back up to 8. 3 up there at 11. All right. You can start to see this V shape. I didn't plot my points very well, but that's okay. You get this V shape. So here is the graph of 3 times the absolute value of x plus 2. All right, so there it is, yay. But we also want to graph the inverse of f on the same grid. Now, you can try to reflect this over that line y equals x, but there is an easier way. Remember, when you do that reflection of line y equals x, you take the y values and the x values and you switch them. So for the inverse, the x values and the y values are going to be switched. So I'm just looking at the table here on the left. What was my y value of 11 now becomes the x value. What was the x value becomes the y value. And we're going to do that all the way down. And now we're going to plot those points. Okay, let's see if we can do this. Nope. Let's see. This was here. Get rid of these dots. Now it's getting closer. Okay, so plotting these points. When x is 11, we got a y value of -3. That's out there. X is 8, y is -2. That's going to be right there. 5, -1, 2, 0. Got back to 5, +1, 8, +2. There's that same V shape, just reflected over that line, y equals x. Okay, is the inverse a function? You should be saying no. You got two reasons now. One is looking at the inverse graph fails the vertical line test. Also looking at the original graph fails the horizontal line test. Okay, but just plotting points like this, one way to graph the absolute value function. I'll show you how to do it in the calculator in class. All right, the last thing here, copy down this top box of information here. It's a thing called a relative error. When we talked about absolute value last time, we had a couple of problems where we talked about how'd they go. You had a certain measurement and you wanted to know what were some allowed values so that the actual measurement was 0.04, within 0.04 of what it's supposed to be. There was a couple problems we did like that. This relative error is actually a percentage. You can only allow a certain percentage to be, the actual measurement to be more or less by a certain percentage. It's called a relative error. And so this equation right here is how you figure it out. And it's a little blurry on my screen. I don't know if it is on yours, but it's x of t minus x over x of t. The x of t, as it says right here, is the object's true value, what it's supposed to be. The value of x is what it actually is. So you take what it's supposed to be minus what it actually is divided by what it's supposed to be. That gives you your relative error. Okay, looking at this example. Certain machine's part's true length is 38.9. So that's your x of t. Centimeters. All right, its length is measured at 39.25. So its actual length is 39.25 centimeters. Find the relative error. Okay, so R of x, relative error, is the absolute value of what it's supposed to be, 38.90, minus what it actually is, 39.25, over its true length, what it's supposed to be. All right, when we do that, we get, let me get a calculator out. Okay, got an absolute value of -0.00899974 and a couple other decimals. So absolute value is going to make that positive. This is a percentage, so we are looking at a positive 0.899%. That is the relative error. Okay, so it's less than 1% off of what it's supposed to be. That's the idea of relative error. That is it. Have a good night. I'll see you in class tomorrow.